almost all of human history, there was one question that sounded, well, kind of stupid to even ask.
And that question was, how fast is light? I mean, seriously, to everyone back then, light didn't really seem to travel at all. It just was.
Think about it for a second. You open your eyes, and boom, the room is immediately lit. There's no delay, no waiting around. Absolutely no sense of anything actually arriving. Light just felt completely instantaneous. It was infinite, unmeasurable, basically just built right into the fabric of existence itself.
And Aristotle? Well, he believed exactly that. He argued that light literally had no speed at all, that it simply existed everywhere at once, the exact moment it was needed. And for nearly 2,000 years, almost nobody seriously challenged him on this. But a few ancient thinkers actually did disagree. Take the Greek philosopher Empedocles around 450 BCE. He proposed something super radical for the time. He said light was something that traveled, that it actually moved through space, and therefore it must take time.
But here's the catch. He had absolutely no way to prove it. I mean, there were literally zero instruments on the planet that could measure something moving that impossibly fast. So it was just a guess. A totally brilliant guess, sure, but completely untestable. And it was destined to remain just a guess for almost 2,000 more years. As we jump forward on this timeline, we see that even the great minds of the Islamic Golden Age weighed in on this. The brilliant scientist Ibn al-Haytham, around the year 1000 CE, argued incredibly passionately that light must have a finite speed. But his argument was based purely on logical reasoning about how human vision worked, rather than actual physical proof.
So, centuries passed. Telescopes were invented, completely unlocking the heavens for us. Gravity was finally explained. The planets were getting mapped out. And yet, still, nobody had actually measured how fast light moved. The bottleneck wasn't a lack of curiosity, not at all. The tools simply didn't exist yet.
Then, right in the early 1600s, one of history's most famously stubborn scientific minds decided, you know what, I'm going to be the one to finally measure this thing. And he was going to do it using nothing but everyday lanterns and a couple of hilltops.
His name, of course, was Galileo Galilei. He and an assistant took lanterns out to distant hilltops in the dead of night. The plan was brilliantly simple. Galileo would uncover his lantern to flash a light, and the exact instant his assistant saw it, they would uncover theirs to flash back. This would theoretically allow Galileo to measure the time in between. It was a remarkably logical setup, but as you might guess, human reflexes are just way too slow, and the experiment ultimately failed. Still, it marks the very first serious, documented human attempt to put a concrete number on the speed of light itself.
And honestly, this is where our story really begins. Not with some massive, triumphant discovery, but with a failure so instructive, it literally set the stage for 3 centuries of increasingly precise measurement. Galileo basically proved that light was just too fast for human hands, which showed future scientists exactly what kind of tools they were going to need to build.
Because what humanity was about to learn wasn't just how fast a beam of light moves. They were actually uncovering a method. They were discovering the universal measuring tape, a way of using light itself to measure the absolute unfathomable scale of the entire universe.
Just think about the sheer grand scale of the cosmos for a minute. Every single star you'll ever look up and see. Every distant, swirling galaxy we've ever managed to photograph. Literally every scientific claim ever made about the exact age of the universe. All of that profound knowledge traces back directly to solving this one singular mystery.
So it all brings us right back to that one deceptively simple problem. How fast does light actually travel? From an ancient radical guess by a Greek philosopher to Galileo standing out in the dark with a lantern, humanity absolutely refused to accept that something was inherently unmeasurable. And honestly, it really leaves you wondering, what other invisible, everyday forces are we currently just ignoring that might hold the key to our next great cosmic awakening? Okay, let's dive into this. You know, for centuries, humanity has looked up at the stars, just completely struck by a seemingly impossible question. How fast does light actually travel? We are looking at a 400-year mystery here, a really relentless quest to literally catch light in the act of moving. Welcome to This Explainer. Today, we're breaking down exactly how scientists managed to pin down the speed of something so incredibly fast that, to our naked eyes, it appears totally instantaneous. And the answer wouldn't come easily. It would take 400 years, dozens of scientists, and increasingly clever experiments to figure this out.
I mean, think about it. They didn't have modern lasers or digital stopwatches at the start. Instead, they had to rely on highly unconventional tools. We're talking about some experiments using complex arrangements of interlocking cogwheels, some using precisely angled rotating mirrors, and some even using the moons of Jupiter itself to track something entirely invisible as it zipped through the darkness of space. Now, what's truly staggering is the definitive result of all that relentless pursuit: 299,792. That is the exact speed of light in kilometers per second. Just wrap your head around that. By the end of this explainer, you'll understand not just that massive number, but exactly how humans proved it using real experiments you can still recreate today. This wasn't some abstract philosophical guess, right? It was derived using logic grounded entirely in the physical world.
So why does pinning down this exact figure matter so much? Well, because this single hard-won number essentially became the foundational ruler. And you'll see how that single number became the ruler used to measure something almost incomprehensibly larger: the size, the age, and the ongoing expansion of the entire observable universe. Literally everything hinges on this one cosmic speed limit. Without it, we'd have absolutely no way to accurately measure the epic scale of reality.
To really understand how we got this universal ruler, we kind of need to initiate a bit of a cosmic flashback. Let's move to where it all began and see how this builds. So let's go back to 1638, to a hillside in Italy, where an aging, half-blind Galileo Galilei attempted the very first scientific experiment to catch light in the act of moving.
Galileo's method was almost embarrassingly simple, at least on paper, especially when you contrast it with the vastness of the universe we were just talking about. This was a wonderfully humble, hilariously low-tech setup. Two people, each holding a covered lantern, would go out into the dark and stand on hilltops roughly 1 mile apart.
And this brilliantly illustrates his logic. Here was the exact game plan. Step 1, the first person on the first hilltop uncovers their lantern, sending a flash of light out into the dark. Step 2, the second person on the far hilltop keeps their eyes peeled, right? Just waiting. And step 3, the moment the second person saw the light, they would immediately uncover their own lantern in response as fast as humanly possible.
So Galileo's plan was basically to measure the time gap between sending the first flash and seeing the second flash return. Because he already knew the exact distance between the two hills, capturing that time gap would allow him to calculate exactly how fast the light had traveled across the distance. It was a seriously elegant idea, and mathematically speaking, his underlying logic was perfectly sound.
But here is the tragic, ironic punchline of this historic attempt. Yes, it was an elegant idea. It was also, unfortunately, totally doomed to fail. And not because the theory was wrong, but because light is simply too fast for human reaction time to measure over such a short distance. I mean, the time it takes for a human eye to register the light, send a signal to the brain, and then tell the hand to uncover a lantern, that is overwhelmingly longer than the fraction of a millisecond it takes light to travel a single mile. Basically, biology completely ruined the math.
Which leaves us with a massive, glaring human bottleneck. Galileo had the right idea, but exactly the wrong biological hardware. So it really begs the question, if human reflexes are fundamentally too slow, how did we finally bypass biology to catch light? How exactly did those later scientists use cogwheels and mirrors and the moons of Jupiter to finally pin down that number of 299,792 kilometers per second? It's a fascinating leap from human error to mechanical precision, and honestly, it is a mystery that will completely change how you look at the night.
Scientific progress as this perfectly straight, clean line. But today, we're looking at a massive breakthrough that arrived over 50 years after the very first theories of light speed. It was 1728, and the evidence came from a source literally nobody expected, a subtle little wobble in starlight itself.
So, let's dive in by asking a pretty fascinating question. What actually happens when a scientific mistake ends up changing history? It is honestly mind-blowing to realize how many of our greatest discoveries happen entirely by accident. You have a researcher looking for one specific thing, and they basically stumble backward into a world-altering truth.
All right, let's jump right into Section 1, the unexpected starlight wobble. Our mystery begins with an English astronomer named James Bradley. Picture this, it's 1728, and Bradley is hard at work observing a star called Gamma Draconis. He was actually attempting to measure stellar parallax, which is just that tiny apparent shift of a star's position caused by Earth's motion around the sun.
He was painstakingly tracking this star night after night, totally expecting to find that perfectly predictable wobble in the sky.
But things definitely didn't go as planned, bringing us to Section 2. A cosmic mystery unfolds.
Instead of confirming his theory, Bradley discovered something else entirely. While he was observing Gamma Draconis over several months, he noticed its position shifted throughout the year for sure, but absolutely not in the pattern that parallax would predict. The shift was in the completely wrong direction and at all the wrong times. It was a total anomaly.
So, how do you solve a cosmic puzzle like that? Let's look at Section 3, the raindrop solution.
Well, eventually, Bradley realized he wasn't looking at parallax at all. He had accidentally discovered a phenomenon we now call stellar aberration. Basically, this is an apparent shift in a star's position caused by the combination of Earth's orbital speed and the finite speed of incoming starlight. Fundamentally, he was proving that incoming starlight isn't instantaneous. It takes real measurable time to arrive.
To really wrap your head around this, think of it literally like rain falling straight down while you run through it. If you're just standing still, the rain hits the top of your head, right? But if you sprint forward, the rain suddenly appears to be coming at a slight angle, hitting you right in the face. And that is purely because of your own motion, not the rain's.
Starlight behaves the exact same way. Because Earth is constantly moving through space and because light takes real time to arrive, we get this apparent shift. The star's position shifts slightly in the sky because the Earth is effectively running through the falling rain of starlight. It's a direct visual fingerprint of light's finite speed.
Now, here is the absolute kicker. By using this aberration effect and Earth's known orbital velocity, Bradley calculated the speed of light with unbelievable precision. I mean, for 1728, he landed within about 1% of the modern accepted value. Just sit with that for a second. Using nothing but telescopes and a wobbling star, he pinned down one of the most fundamental constants of physics.
Which perfectly sets up Section 4, Chasing Light in the Lab. This discovery was a massive leap forward. It wasn't just a better number, it was a completely independent method using a totally different phenomenon that confirmed Ola Roemer's basic conclusion from decades prior. Think about it. With Roemer, it was a wobbling moon around Jupiter. With Bradley, it was a subtle shift in distant starlight. Two completely different astronomical techniques had now arrived at strikingly similar answers.
But here's the catch, and it's a big one for the history of science. Both of these methods still relied on the massive scale of the cosmos. They depended entirely on astronomical distances, observing things happening millions of miles away, far outside of Earth's atmosphere.
Which leaves us with a profound question to end our explainer on. How would the next generation of scientists do something nobody had managed yet and measure the speed of light completely inside a laboratory on Earth? How do you capture the fastest moving thing in the universe and measure its speed within the confines of a single...
Absolutely thrilled you're here with us today because, well, we're going to unravel a true cosmic mystery. We're going way back in time to look at a singular, mind-blowing observation that quite literally overturned 2,000 years of firmly established human thought. We're going to explore how humanity figured out one of the most fundamental truths of our entire universe, and they did it just by looking up at the night sky. So let's jump right in. Here is the massive, heavy, philosophical question that the world's absolute brightest minds had been arguing over for 2 millennia. Is light instantaneous? Like when you strike a match or when the sun comes up in the morning, does that light reach your eyes instantly? Does it just have this infinite speed, existing everywhere all at once the exact moment it's created? For 2,000 years, the assumption was an undeniable, rock-solid yes. Light was thought to be instantaneous. But, as we're about to see, the universe had a very different answer waiting for us.
Part 1. The Jupiter Eclipse Anomaly.
Okay, so this is where our detective story really kicks off, with a weird mathematical clue hiding right there in the dark. Astronomers back then were diligently tracking the moons of Jupiter, specifically this one moon named Io, as it orbited and eclipsed behind the giant planet. But the math, it just wasn't adding up. The timing of these eclipses was acting incredibly strange. See, when Earth was closer to Jupiter in its orbit, the eclipses happened earlier than predicted. But when Earth was farther away, positioned way on the opposite side of the sun, the eclipses happened later. So the timing depended entirely on where Earth was in its orbit.
Part 2. A radical new hypothesis.
Enter our lead detective for the day, the Danish astronomer Ole Roemer. He looked at this bizarre discrepancy, and he saw something completely revolutionary. Roemer had a radical insight. He thought, well, what if the delay wasn't a flaw on the prediction at all? What if it was simply the time it took light to physically cross the extra distance to Earth? If Earth is further away, the light from Jupiter's moon has to travel further to reach our telescopes. Romer hypothesized that this delay was actually the literal travel time of light itself.
Part 3. The 10-minute prediction.
Now, having a brilliant idea is one thing, right? But proving it to a highly skeptical scientific establishment, that is a whole different ballgame. In 1676, Romer presented his findings to the prestigious French Academy of Sciences. He argued, boldly, that light did not travel instantly, and to prove it, he put his whole reputation on the line. He predicted that a specific upcoming eclipse of Jupiter's moon Io would arrive exactly 10 minutes late. Naturally, many astronomers were super skeptical. I mean, instant, infinite speed light had been the absolute assumption for 2,000 years. But when the predicted date finally arrived, Io's eclipse showed up exactly as Romer had calculated, exactly 10 minutes behind schedule. It was a stunning, testable, and completely repeatable proof. Light was not instantaneous. It had a real, measurable, finite speed. And for the very first time in human history, someone had actually proven it experimentally.
Part 4. The first real number.
So, now that the world knew light actually had a speed, the immediate next question was super obvious. Exactly how fast is it? Scientists needed to turn this dramatic 10-minute delay into a concrete mathematical calculation. Based on his observations, Romer estimated that light took roughly 22 minutes to cross the entire diameter of Earth's orbit around the Sun. To put that massive scale into perspective, that orbit distance is about 300 million kilometers. Using that figure, the brilliant Dutch physicist Christian Huygens sat down to do the math, and he calculated the first ever numerical estimate for the speed of light, roughly 220,000 kilometers per second. Just let that sink in for a second. Over 200,000 kilometers in a single second. Now, what's really interesting here is that that number was actually too low. It was off by about 26% from the true, precise value we know today. But we really have to remember the context here. Given 17th century instruments, this was an extraordinary achievement. It was the very first real number ever attached to light speed.
Part 5. Humanity's Cosmic Ruler.
The legacy of what Romer and Huygens achieve goes so far beyond just a single number. For the very first time in recorded history, humanity had a measurable, science-based answer to a question philosophers had argued about for 2,000 years, and they figured it out entirely by watching a moon disappear and reappear behind a planet. But Romer's method proved something enormously important beyond just the number itself. It proved that astronomical distances could be used as measuring tools, when earthbound distances were simply too small to work with. You couldn't just measure the speed of light in a 17th century laboratory. It was way too fast. You needed the vast space of the solar system to act as a natural ruler. And this idea, using vast cosmic distances as a kind of natural ruler, would echo through the rest of this story, all the way up to how we measure the vast size of the universe today.
Which brings us to a really fascinating turning point. Romer's number, while incredibly historic, was still rough. Scientists knew they needed sharper, more precise methods and more direct evidence based on something other than distant planetary eclipses. The finite speed of light was proven, but the quest for absolute precision had just begun. What ingenious methods would scientists invent next to pin down the universe's ultimate speed limit? Well, that is a fantastic question, and one I really hope you're eager to explore further. Thank you so much for joining me for this explainer. Keep looking up and keep asking questions.
You know, we often picture scientific progress as this perfectly straight, clean line. But today, we're looking at a massive breakthrough that arrived over 50 years after the very first theories of light speed. It was 1728, and the evidence came from a source literally nobody expected, a subtle little wobble in starlight itself.
So, let's dive in by asking a pretty fascinating question. What actually happens when a scientific mistake ends up changing history? It is honestly mind-blowing to realize how many of our greatest discoveries happen entirely by accident. You have a researcher looking for one specific thing, and they basically stumble backward into a world-altering truth.
All right, let's jump right into Section 1, the unexpected starlight wobble.
Our mystery begins with an English astronomer named James Bradley. Picture this. It's 1728, and Bradley is hard at work observing a star called Gamma Draconis. He was actually attempting to measure stellar parallax, which is just that tiny apparent shift of a star's position caused by Earth's motion around the Sun.
He was painstakingly tracking this star night after night, totally expecting to find that perfectly predictable wobble in the sky.
But things definitely didn't go as planned, bringing us to Section 2. A cosmic mystery unfolds.
Instead of confirming his theory, Bradley discovered something else entirely. While he was observing Gamma Draconis over several months, he noticed its position shifted throughout the year for sure, but absolutely not in the pattern that parallax would predict. The shift was in the completely wrong direction and at all the wrong times. It was a total anomaly.
So, how do you solve a cosmic puzzle like that? Let's look at Section 3, the raindrop solution.
Well, eventually, Bradley realized he wasn't looking at parallax at all. He had accidentally discovered a phenomenon we now call stellar aberration. Basically, this is an apparent shift in a star's position caused by the combination of Earth's orbital speed and the finite speed of incoming starlight. Fundamentally, he was proving that incoming starlight isn't instantaneous. It takes real measurable time to arrive.
To really wrap your head around this, think of it literally like rain falling straight down while you run through it. If you're just standing still, the rain hits the top of your head, right? But if you sprint forward, the rain suddenly appears to be coming at a slight angle, hitting you right in the face. And that is purely because of your own motion, not the rain's.
Starlight behaves the exact same way. Because Earth is constantly moving through space and because light takes real time to arrive, we get this apparent shift. The star's position shifts slightly in the sky because the Earth is effectively running through the falling rain of starlight. It's a direct visual fingerprint of light's finite speed.
Now, here is the absolute kicker. By using this aberration effect and Earth's known orbital velocity, Bradley calculated the speed of light with unbelievable precision. I mean, for 1728, he landed within about 1% of the modern accepted value. Just sit with that for a second. Using nothing but telescopes and a wobbling star, he pinned down one of the most fundamental constants of physics.
Which perfectly sets up Section 4, chasing light in the lab. This discovery was a massive leap forward. It wasn't just a better number, it was a completely independent method using a totally different phenomenon that confirmed Ola Roemer's basic conclusion from decades prior. Think about it. With Roemer, it was a wobbling moon around Jupiter. With Bradley, it was a subtle shift in distant starlight. Two completely different astronomical techniques had now arrived at strikingly similar answers.
But here's the catch, and it's a big one for the history of science. Both of these methods still relied on the massive scale of the cosmos. They depended entirely on astronomical distances, observing things happening millions of miles away, far outside of Earth's atmosphere.
Which leaves us with a profound question to end our explainer on. How would the next generation of scientists do something nobody had managed yet and measure the speed of light completely inside a laboratory on Earth? How do you capture the fastest moving thing in the universe and measure its speed within the confines of a single room? It's a huge question, so keep it in mind, because the evolution of human discovery never truly stops. Thanks so much for joining me today.
We know the speed of light? It's one of those fundamental constants we totally take for granted today. But finding that number? Oh, that was not easy. Let's jump right into how 19th century physicists measured it using incredibly simple, elegant mechanical tools right here on Earth. I mean, seriously, how do you even measure the fastest thing in the universe? Think about it for a second. How is it physically possible to catch something moving seemingly instantaneously? You turn on a flashlight, and that beam hits the wall before you even have a chance to blink. For centuries, this was a monumental scientific mystery. People thought trying to measure its speed was a literal fool's errand because human reflexes simply cannot compete with the speed of illumination.
Looking at the timeline, you can see the progression. Back in the mid-1600s, Galileo actually tried to figure this out with a lantern experiment on a hillside. Spoiler alert, it totally failed. Light is simply way too fast. But then, look at the 1800s. We went from those failed hillside lanterns to successful, ingeniously simple laboratory experiments in the span of just a couple of years.
Section 1. Racing the speed of light, the impossible challenge of capturing instantaneous motion. So, if human reaction time is the roadblock, the solution is pretty obvious, right? We have to remove the human entirely. To capture something moving faster than our biology can process, we needed a machine. That massive breakthrough finally came in 1849 from a French physicist named Hippolyte Fizeau. Fizeau realized he had to build a mechanical trap for light. It's widely considered one of the most ingeniously simple experiments in the entire history of physics. His solution didn't involve complex modern electronics or sensors. No, It involved a spinning, toothed wheel.
Moving to the mechanics. The spinning toothed wheel. Fizeau's ingenious 1849 experiment in Paris.
Fizeau essentially turned mechanical engineering into a time machine. But he knew he couldn't just do this on a standard laboratory table. Light is too fast for that. He needed a massive runway. So he actually set up his apparatus between two high elevations near Paris, Surennes and Montmartre. These two hills were separated by a real, carefully measured distance of about 8 kilometers. He absolutely needed that vast gap just to give the light enough travel distance so its time would actually be perceptible to his machine.
Here's how this brilliantly simple binary mechanic worked. Step 1, Fizeau shines a bright beam of light right through the gap of a rapidly rotating toothed wheel. Step 2, the light travels the full 8 kilometers to a distant mirror on the other hill, bounces off, and speeds back. And step 3, here is the genius part. Because the wheel is spinning at certain precise rotation speeds, the returning light would pass cleanly back through a gap, and Fizeau would see it. But at other speeds, a tooth would rotate perfectly into the path and block the returning light entirely. It would literally vanish from his view. By precisely controlling the wheel's rotation speed and calculating exactly how fast it needed to spin to block that light, Fizeau could calculate exactly how long the light's 16-kilometer round trip had taken. The math revealed an astonishing result. Approximately 313,000 kilometers per second. I just want you to pause and appreciate that for a second. That is remarkably close to the true value. And he achieved this mind-bending calculation using nothing but a spinning wheel, a mirror, and a measured distance between two French hills. Just pure, brilliant deduction. And this was historic for one specific reason. Prior to Fizeau, our only rough estimates came from astronomers observing Jupiter's moons. It was entirely celestial. This was the very first measurement of light speed done entirely on Earth. He took this cosmic measurement and brought it down into a terrestrial setting. It proved we could measure the universe's fundamental constants using our own tools.
Part 3. The Rotating Mirror Upgrade. Enter Leon Foucault and the Pursuit of Precision.
You know how science works. Once a barrier falls, the race for perfection is immediately on. Just one single year later, in 1850, a rival French physicist named Leon Foucault enters the picture. Foucault essentially thought, I can do this better, and I can do it smaller. He refined the method by completely ditching the toothed wheel, swapping it for a rapidly rotating mirror. The light would bounce off the spinning mirror, head to a stationary mirror, and reflect back. But because that primary mirror was rotating so incredibly fast, by the time the light returned, the mirror had turned by a microscopic angle. This made the light hit a slightly different spot. By measuring that tiny deflection angle, Foucault could calculate the speed. It was a technique that allowed for way greater precision. This perfectly illustrates the leap in accuracy. Fizeau started out at roughly 313,000, but Foucault's rotating mirror brought the measurement down to around 298,000 kilometers per second. Compare that to the modern accepted figure of 299,792, achieved with highly advanced lasers and atomic clocks. Foucault was astonishingly close. It is absolutely wild that he achieved this level of precision with mid-19th century equipment.
Part 4. Settling the Great Debate. How measuring speed changed the laws of physics.
Now this is where the story gets super fascinating. Foucault didn't just want a number on a speedometer. He realized his incredibly precise apparatus was the perfect tool to settle a completely separate, centuries-old scientific debate. Physicists had been warring over the fundamental nature of light. Isaac Newton argued light was made of particles. Others argued it with a wave. A key battleground here was how light behaved in different mediums. The particle theory actually predicted light should travel faster through a dense medium like water, but the wave theory predicted the exact opposite, that it would be slower in water than in air. So, Foucault shoots one beam of light through the air and another right through a tube of water. The result? Totally definitive. Foucault proved beyond a shadow of a doubt that light demonstrably moves slower in water than in air. He could literally physically measure the delay using the deflection angle of his spinning mirror. And because he proved it moves slower in water, his findings directly supported the wave theory of light over the competing particle theory of the time. Think about the gravity of that. With an apparatus made of glass and gears, Foucault didn't just measure a constant, he settled a major scientific dispute. He shifted our fundamental understanding of physics. By the mid-1800s, humanity had literally gone from Galileo staring helplessly at a lantern on a hill to fundamentally proving the wave-like nature of reality right in a laboratory. Which brings us to a final, really intriguing question.
If they could measure the speed of light with a simple spinning wheel and a mirror in 1849, what impossible thing could we measure today? It really makes you step back and marvel at human ingenuity. The tools might change, but that relentless drive to quantify the universe is exactly the same. Thank you so much for joining me on this explainer. I hope this illuminated just how beautifully simple some of science's greatest discoveries really were. Keep questioning the impossible, and I'll see you next time.
Most of us are perfectly happy with close enough. I mean, it gets the job done, right? But today, we are diving into the absolutely thrilling 50-year quest of a guy who looked at the universe's ultimate speed limit and completely refused to accept that phrase. We're talking about the speed of light, something so incomprehensibly fast that measuring it literally seems like a task for the gods. Yet one scientist made it his absolute unrelenting obsession to pin that exact number down. Seriously, I want you to imagine, just for a second, dedicating nearly 5 decades of your life to one single goal. And not just a broad field of study either, but obsessively refining one single, seemingly impossible measurement. Look, most of us get impatient waiting for the microwave to finish, right? But imagine pouring that insane level of dedication into just one answer. What actually happens when you refuse to accept close enough? What happens when you dedicate your entire professional existence to chasing a number that dictates the very rules of the cosmos? Okay, let's dive into this. The man we're talking about was Albert Michelson. He was a U.S. Naval Academy graduate turned physicist, and he didn't just have a passing interest in light. Oh no, he spent nearly 50 years of his career obsessively refining the measurement of its speed. He basically brought the super strict discipline of the Navy right into the laboratory, applying this intense, singular focus to achieve a level of precision the scientific world had literally never seen before. So to really understand the sheer scope of his obsession, we got to map out his journey, starting way back in 1878. He began building these increasingly sophisticated versions of Foucault's rotating mirror experiments. Basically, he was trying to catch a bouncing beam of light using incredibly fast spinning glass. Now, he had some major early success in 1879, but that didn't satisfy him. Actually, it only fueled a decades-long desire for even greater accuracy, a journey that would lead to a Nobel Prize and eventually his mind-blowing mountain experiment in 1926. Now, what's really interesting about this slide is his early result. In 1879, he published his findings, and the number was 299,910 kilometers per second. Just think about that for a minute. Using 19th century technology, he calculated a speed that is remarkably close to today's accepted number. Honestly, for almost anyone else, this would be the crowning achievement of a lifetime. They'd take their accolades, pack it up, and retire. But not Michelson. No way. Michelson was definitely not finished. Over the following decades, he essentially looked at his incredibly precise equipment and kept asking, okay, how can I make this even better? He relentlessly upgraded his tools again and again. We're talking using much longer distances to test the light, building better, more flawless mirrors, and developing infinitely more precise timing mechanisms. He was just constantly pushing the very boundaries of physics. And this brilliantly illustrates where all that obsession led. This pursuit culminated in 1926 with an experiment of just staggering scale. He didn't just use a lab anymore. He used the actual geography of the Earth. He stretched a light path between Mount Wilson and Mount San Antonio out in California. That's a distance of roughly 35 kilometers. By spinning a specially built octagonal mirror at extremely high, precisely controlled speeds, he literally timed the light's journey across that massive mountain range and back. So, what was the result of that breathtakingly complex journey across the California mountains? 299,796 kilometers per second. That's the number. It's a figure so incredibly precise, so mind-bogglingly close to today's accepted value that it stood as one of the most accurate measurements achieved for years afterward. All those decades of absolute obsession had finally paid off. Now, you might think this huge 1926 triumph is what finally put him on the map, right? But the scientific world had actually recognized his genius long before that. Back in 1907, Michelson became the very first American to win the Nobel Prize in a scientific field. The award was largely for his meticulous precision work on light and optical instruments. It proved his whole methodology was already changing the scientific world well before his mountain experiment. So the crucial point is that Michelson's 50 years of obsession gave us far more than just some accurate number for textbooks. His life's work proved something absolutely essential. The speed of light wasn't just fast, it was fixed, it was consistent, and it was measurable with staggering precision, totally regardless of the direction or the specific method used to test it.
It was an absolute unmoving constant. But here is where the story takes a massive, massive twist. By establishing that light is this absolute fixed constant, Michelson accidentally created a huge problem for the rest of physics. I mean, think about it. If the speed of light never ever changes, then the things scientists previously thought were absolute, like space and time themselves, well, they couldn't be. They had to be flexible. They had to be completely reevaluated from the ground up.
And that exact consistency, that rigid, unbreakable number Michelson spent 50 years hunting down, turned out to be one of the most important facts in all of physics. Why? Because it directly inspired a young patent clerk in Switzerland to literally question everything scientists thought they knew about space and time. Yep, we're talking about Albert Einstein. Michelson's precision is what forced Einstein to rethink reality, leading directly to the theory of relativity.
A 50-year obsession with a single measurement didn't just refine a number on a chalkboard, it completely rewrote the fabric of reality. So ask yourself, if pinning down one fixed number can...
Not just as some fun piece of bar trivia. We're going to explore how a really strange scientific mystery completely transformed into the absolute foundation of human measurement. We're talking about an obsessive quest that literally revolutionized how we understand reality itself.
So, to get us started, I want you to think about a seemingly simple question. How long is a meter really? If I asked you to show me, you'd probably, hold your hands apart or maybe picture one of those wooden meter sticks from a high school science class. It feels like a totally mundane, everyday physical object, right? Just a fixed distance we use to measure our tables, our rooms, basically our entire world. But the reality of what that distance actually represents, well, it's rooted in something way more profound than a piece of wood.
The story of how we actually define that distance takes a massive turn with a very famous face. Yep, that patent clerk was Albert Einstein. In 1905, building partly on the frankly strange consistency of light's measured speed, he published his theory of special relativity. Einstein proposed something truly radical. He argued that the speed of light is the same for every observer, no matter how fast they themselves are moving. Think about that for a second. If you're standing completely still, or if you're flying in a rocket at half the speed of light, light still races away from you at the exact same relative speed. It's a fixed cosmic speed limit built into the very fabric of reality itself.
And this single idea reshaped physics entirely. It led to mind-bending concepts like time dilation, mass-energy equivalence, and our modern understanding that absolutely nothing with mass can ever reach, let alone exceed, the speed of light. So light speed isn't just fast, it's the ultimate, absolute boundary of our universe.
Which brings us to the chase. Centuries of relentless measurement.
Because Einstein didn't just pull this idea out of thin air, right? It all traced back to careful, repeated, real-world experiments. We're talking about Roemer's Jupiter moon observations, Bradley's starlight aberration, Fizeau's toothed wheel, Foucault's mirror, and of course Michelson's decades of absolutely relentless precision work. Then, by the 20th century, scientists had refined the number again and again, using increasingly advanced technology. We're talking lasers in the 1960s, atomic clocks in the 1970s, and eventually massive particle accelerators.
And the crazy part? Each new method converged on the exact same value. They were tightening the margin of error decade after decade until the number became one of the most precisely known constants in all of physics. They had finally, actually pinned light down.
So, here is the plot twist. The historic 1983 decision.
Finally, in 1983, the international scientific community made a historic decision. Up until then, they had been continuously measuring the speed of light, treating it as this physical phenomenon to be approximated with tiny margins of error. But that year, they didn't just measure the speed of light anymore. They defined it permanently as an exact number.
That number is 299,792,458 meters per second. I mean, really let that sink in. It is not an approximation. It is not a measurement with a margin of error. It is an internationally agreed, exact, fixed definition, the absolute anchor of our reality.
So how does this circle back to that question I asked you at the very beginning? What is a meter? Well, in fact, the modern definition of the meter itself is now based on the speed of light. It's officially defined as the distance light travels in a specific, precise fraction of a second.
So today, when we say light travels at basically 299,792 kilometers per second, we're not quoting a measurement anymore. we're quoting the very foundation of how humanity defines distance itself. Literally everything you interact with, the distance from your eyes to the screen you're looking at, the width of the room you're sitting in, the miles between you and your family, all of it is tethered completely to this singular universal constant.
It kind of changes how you look at the world, doesn't it? Which leaves us with this final thought. If our very concept of physical distance, like the most basic foundational way we measure our reality, is actually built on the speed of light, what else about our reality is hiding in plain sight? Next time you measure something, remember, you're actually holding a tiny fraction of the cosmic speed limit right in your hands.
Seriously fascinating documentary that highlights a massive turning point in human history. So at this point, we know with total certainty exactly how fast light travels, right? But what this is really about isn't just that specific number. It's about what humans actually did with it next. To really wrap our heads around the sheer scale we're dealing with today, we've got to start with this absolutely mind-boggling number, 9.46 trillion. That is the exact amount of kilometers that light travels in a single standard Earth year. And honestly, pinning down this exact distance, it was basically like handing early astronomers the keys to the universe. Which brings us to Section 1, the Universal Measuring Tape.
See, once you know exactly how fast light moves, you unlock something pretty extraordinary. You gain the ability to use light itself as a literal measuring tape for the entire universe. The logic here is super straightforward. If light takes a certain amount of time to reach you, and you already know exactly how fast it's going, well, simple multiplication tells you exactly how far away its source must be.
Moving on to Section 2, decoding the light year.
This simple mathematical reality is the exact principle behind the light year, and this is crucial. Despite having the word year right there in its name, it's absolutely not a measurement of time. It's a measurement of distance, literally, how far light travels in one full year. So 1 light year equals about 9.46 trillion kilometers. And once scientists had light speed locked down so precisely, they finally had, for the very first time, a completely reliable tool to measure truly cosmic distances.
But there's a catch. Section 3, the distance dilemma.
Our cosmic detectives almost immediately hit a massive roadblock. You see, light years only really work as a measuring tool if you already know how long the light took to reach you in the first place. And for the vast majority of objects out there in deep space, that's just not obvious at all.
They were kind of stuck. Astronomers desperately needed an entirely separate technique. They needed a way to figure out the actual physical distance to stars and galaxies, completely independent of just guessing how long their light had been traveling. And that leads us to Section 4. The parallax solution. The first real breakthrough here was actually a method astronomers had been attempting since ancient Greece, but they only successfully pulled it off in the 19th century. It's called stellar parallax. The core idea is super simple, and you can actually test a version of it yourself right now, wherever you are. Seriously, try it. Hold your finger up, close one eye, and then switch eyes. You'll notice your finger appears to jump or shift against the background of the room. Notice how the closer your finger is to your face, the bigger that apparent shift is. And if you move it farther away, the shift gets smaller. Well, that's parallax in action. And the crazy thing is, it works exactly the same way with stars. So let's scale this up to the size of the solar system. As Earth orbits the sun, nearby stars appear to shift very, very slightly against the background of much more distant stars. We just have to look at them from opposite points in Earth's orbit, exactly 6 months apart. Those 2 points basically become our 2 eyes. By incredibly carefully measuring that tiny, tiny angular shift and combining it with the exact diameter of Earth's orbit, astronomers can calculate the star's precise distance. And they do it just using straightforward trigonometry. They essentially used our own solar system's geometry to anchor the rest of the cosmos. I mean, think about the sheer ingenuity of that for a second. Using the physical movement of our own rock flying through space, combined with basic high school math, to reach out and literally measure the infinite. It's a realization that should make us all look up at the night sky with a profound sense of wonder. If we figured out how to measure the universe with a simple triangle, well, what other incredible secret—
Back to the explainer. So, you know that feeling when you look up at the night sky and try to wrap your head around just how far away all those stars actually are? Well, for centuries, humanity literally had no clue. It was just this beautiful, totally unmeasured void. But today, we're diving into exactly how we finally nailed down the true physical scale of the cosmos. We're going to trace this monumental breakthrough, starting with one seriously determined astronomer and ending with an absolute unsung hero who completely rewired our understanding of space. Let's get into it.
All right, 1838. This is the year things get real. A German astronomer named Friedrich Bessel decides he's going to be the first person to actually measure a star's distance. He sets his sights on this kind of faint star called 61 Cygni. Up until this exact moment in history, nobody had successfully pulled this off. The distances were just too vast. But Bessel was totally determined to change that, and spoiler alert, he was about to secure a massive, massive first in human history.
So how do you do it? He used a method called parallax. Now, if you're familiar with the concept, you know parallax relies on measuring that incredibly slight, apparent shift in a star's position as the Earth orbits the Sun. It's like closing one eye then the other and watching your thumb jump across the background. By painstakingly tracking this tiny shift, Bessel successfully calculated a stellar distance for the very first time. I mean, what a staggering achievement, right? He basically yanked the universe out of the realm of pure philosophy and dragged it right into hard, measurable math.
But here's the part that is just truly mind-blowing, the sheer accuracy he achieved with 1838 tech. We're talking manual, on-paper calculations and hand-ground telescopes. Bessel crunches the numbers and gets a distance of roughly 10.3 light-years for 61 Cygni. Today, with all our insanely precise modern instruments, we measure it at about 11.4 light-years. Just think about that for a second. With hand-ground glass and scratch-pad math, he was incredibly close. It's an absolutely extraordinary result.
So this measurement proved, for the first time ever, a real, calculated, physical distance to another star. And why is that such a game changer? Because it wasn't just some rough estimate. It wasn't a guess. It was a genuine, testable number. After centuries of literally just guessing, humanity finally had a concrete, physical measurement to anchor us to the wider cosmos.
But, yeah, there's a but. As incredible as Bessel's breakthrough was, it immediately opened up a brand new, glaring problem. What happens when stars are thousands of light years away? It's the critical question here. Bessel proved we could measure our immediate next-door neighbors, sure, but the deeper astronomers tried to peer into the dark, the more they realized they were hitting an absolute brick wall.
You see, parallax has a hard limit. The geometric angles involved just become way too tiny to measure accurately once a star is more than a few hundred light years out. The method literally breaks down. It just fails. And, as astronomers were very quickly starting to realize, the universe is unimaginably larger than a few hundred light years.
So they needed a completely different method, right? Something that could reach far, far beyond the limits of parallax. And the real breakthrough here, it didn't come from some famous professor at the eyepiece of a giant telescope. Nope, it came from a woman working quietly at Harvard. Her name was Henrietta Swan Leavitt. In the early 1900s, she was working at the Harvard College Observatory, hired along with several other women simply to catalog photographic plates of the night sky.
And we really have to talk about this setup here, because the contrast is stark. Leavitt and her female colleagues were paid far less than the male astronomers, and they were basically barred from actually using the telescopes directly. Instead, their job, their incredibly demanding, tedious job, was to painstakingly measure star brightness on thousands of glass photographic plates, entirely by hand, just hunching over glass day in and day out.
But here is the amazing part. Despite these immense constraints, working with just magnifying glasses and glass plates, Leavitt made one of the most important discoveries in the entire history of astronomy. I'm not exaggerating. She found the key that would eventually reveal the true scale of the universe in a way Bessel couldn't have even dreamed of.
To get what she did, we need to look at what she was studying. Leavitt was zeroed in on a specific type of star called a Cepheid variable. These are stars whose brightness rhythmically pulses. They brighten and dim over a very regular, repeating cycle. You can think of them almost like cosmic lighthouses, just reliably flashing out there in the dark.
So let's walk through her logic. She focused her observations on a bunch of these Cepheids located in a nearby galaxy called the Small Magellanic Cloud. She tracked that rhythmic brightening and dimming cycle over and over across thousands of those glass plates. And by meticulously comparing all of this data she calculated entirely by hand, remember, she uncovered this remarkable pattern that literally no one else had noticed. And this right here, this is the massive climax of the explainer. Leavitt noticed that the brighter a Cepheid actually was, the longer its pulsing cycle took. That's it. It sounds so simple, but it is profoundly powerful. Because once she proved this link,
Astronomers could figure out a star's true brightness just by timing its pulse. Then they just compare that true brightness to how dim it appears from Earth, and boom, you can calculate the exact distance. It was the absolute perfect solution to the parallax problem. By unlocking the secret of these Cepheid variables, Leavitt handed astronomers the exact tool they needed to measure the deep cosmos. Humanity was finally reaching far beyond the limits of parallax. We were no longer stuck in our tiny local neighborhood of just a few hundred light-years. Thanks to Leavitt's direct correlation, we could now measure those vast, mind-bending distances across an unimaginably large universe.
It really makes you step back and think, doesn't it? From Bessel manually calculating our very first step into the cosmos in 1838 to Henrietta Swan Leavitt silently breaking open the entire universe from a desk covered in glass plates. So I want to leave you with this one final thought for today. If a woman barred from telescopes could map the stars, what other universe-altering discoveries are hiding in plain sight? Thanks for joining me for this explainer.
I'm absolutely thrilled to share this one with you because we're looking at one of the most profound shifts in human history. We are going to explore how a single, elegant mathematical relationship discovered in the early 1900s literally changed astronomy forever. Just by looking at the rhythm of the stars, humanity unlocked the true scale of the cosmos. So, let's get started.
It's an incredibly daunting question, isn't it? I mean, how do you even begin to measure a universe when you can't see the end of it? For the longest time, astronomers faced this immense challenge. Traditional methods, like parallax, worked well enough for objects relatively close to Earth, but as astronomers tried to look deeper into the dark ocean of space, well, those methods completely failed. They simply could not reach far enough. To measure the true depths of the universe, science desperately needed a completely new tool.
Section 1. The period luminosity relationship. Okay, let's dive right into this, because the solution didn't come from a giant new telescope, but from the brilliant mind of an astronomer named Henrietta Swan Leavitt. She studied the stars and noticed a distinct mathematical pattern. This became known as the period luminosity relationship, published by Leavitt in 1908 and refined further by 1912, and it changed astronomy forever.
To really understand her discovery, we have to look at what she was actually studying. You see, Leavitt wasn't just looking at any random stars. She was specifically studying what are called Cepheid variables. These are highly unique stars because they pulse. They grow brighter and dimmer in this very regular, predictable rhythm. And that pulse, that heartbeat of the star, contained the secret mechanism that would eventually unlock the size of the entire universe.
Section 2. Measuring standard candles. So let's take a look at how identifying that pulse actually works as a mechanism for measuring distance.
Because of her incredible work, Cepheid variables became what astronomers call standard candles. Reliable, known brightness reference points scattered throughout the universe, usable to measure distances far beyond where parallax could ever reach. You can kind of think of a standard candle like a cosmic lighthouse, or a highly reliable mile marker on a really dark highway. Because you know exactly how bright that lighthouse actually is at its source, you can figure out how far away it must be just based on how faint its light appears to your eye. And here's why it mattered so enormously. If you can measure a Cepheid's pulse period, you instantly know its true actual brightness, regardless of how far away it is. Let that sink in. And once you know a star's true brightness, comparing it to how dim it actually appears from Earth lets you calculate exactly how far away it must be, using a simple, reliable formula. It was a literal aha moment of cosmic calculation. The absolutely crucial takeaway here is that astronomers were suddenly no longer confined to our immediate cosmic neighborhood. Just like we talked about, these standard candles were usable to measure distances far beyond where parallax could ever reach. They finally had a reliable ruler, a true measuring stick to gauge the deep, deep universe. Section 3. An unrecognized genius. But you know, as fascinating as the science is, we really have to pivot here to look at the tragic lack of recognition for the absolute genius who gave us this universe-shattering tool.
Just take a look at this heartbreaking timeline. Leavitt refines her incredible method in 1912, but sadly, she passes away a few years later. In fact, a Swedish mathematician later attempted to nominate Leavitt for a Nobel Prize in 1925, only to discover she had already passed away 4 years earlier. Nobel Prizes cannot be awarded posthumously.
Leavitt's discovery didn't get the recognition it deserved during her lifetime. She died in 1921, largely uncredited by the broader scientific community for a method that would soon transform our understanding of the cosmos. She opened a massive door to the universe, but she wouldn't live to see what was on the other side. Section 4. Expanding the universe. Now, moving forward to the 1920s, let's see how this next great leap in cosmic measurement actually played out.
But her method became the essential tool for the next great leap in cosmic measurement, used almost immediately by an ambitious young astronomer working at Mount Wilson Observatory in California. That astronomer's name was Edwin Hubble, and in the 1920s, he pointed the largest telescope in the world at a fuzzy, cloud-like object then known as the Andromeda Nebula.
Now, what's really interesting about this is the contrast between what humanity thought it knew and what Hubble was about to prove. At the time, most astronomers believed the Andromeda Nebula was a relatively nearby cloud of gas and dust existing entirely within our own Milky Way galaxy, which scientists then believed was the entire universe. That was it. That was the boundary of reality. But Hubble's discovery shattered that old belief completely.
So, how exactly did he prove it? Well, using Leavitt's period luminosity method, Hubble identified Cepheid variable stars inside Andromeda. By measuring their pulse and calculating their true brightness compared to their apparent dimness, the math proved undeniable. Andromeda wasn't just some nearby gas cloud. It was an entirely separate galaxy positioned vast, unimaginable distances outside our own Milky Way. Thanks to Leavitt's standard candles, the universe was suddenly much, much bigger than anyone had ever dreamed.
It's just an awe-inspiring story of human ingenuity, isn't it? A single mathematical observation about pulsing stars literally cracked open the infinite scale of reality. But it does leave us with a lingering, provocative thought. How many other universe-altering discoveries were made by unsung heroes who never lived to see their impact? Henrietta Swan Leavitt.
We are diving into what is, honestly, one of the most mind-bending detective stories in the entire history of science. We're going to explore how humanity figured out not just that our universe had a starting line, but exactly how we learned to measure its incredibly vast scale. And you know, it all starts with this massive, grand aha moment. I mean, for centuries, people looked up at the stars and just kind of wondered about the nature of the cosmos. But it wasn't until Georges Lemaitre's brilliant theoretical work was combined with Edwin Hubble's real, physically measured data that everything finally clicked into place. The combination of these two elements gave rise to arguably one of the most important conclusions in the history of science. The universe had a beginning.
Okay, let's dive into this, because this is where the logic gets really fascinating. Hubble's real-world data showed us that galaxies are moving apart today, right? The universe is actively expanding. So what happens if we rewind the cosmos? If galaxies are moving away from each other right now, running the clock backward means they must have all been closer together in the past. And if you keep rewinding, eventually all that matter, all those galaxies must converge at a single point. That point represents the very beginning of time and space itself. It's a simple deduction for sure, but a totally world-changing one.
Section 1. The ultimate deduction. A universe with a beginning. So in a stunning full circle, the exact same toolset of careful, repeated physical experimentation used to measure things like the speed of light had now led humanity to actually measure the birth of the entire universe itself.
Section 2. The accidental brand, naming the cosmos. Now, you'd think a paradigm-shifting discovery like this would get a highly technical, prestigious Latin name, right? Well, the reality is actually pretty funny. Now, what's really interesting about this slide is the sheer irony of the whole situation. The idea that all of time and space exploded outward from a single point was actually highly controversial at first. The term Big Bang was coined by a rival scientist who fundamentally disagreed with the theory. They nicknamed it the Big Bang, somewhat dismissively, intending it to be a complete insult to just mock the whole concept. But beautifully, the name was so incredibly catchy that it stuck permanently. The insult became the official world-renowned brand for the birth of our universe. Section 3. Hitting the distance wall, the limits of our tools. So, scientists knew there was a beginning, but to figure out exactly how old the universe was and exactly how big it had become, they needed better measuring tools.
Up to this point, astronomers used Cepheid variable stars as their standard candles. These are objects with a known true brightness that let us calculate distance based on how dim they appear to us. But we hit a massive cosmic brick wall at roughly 100 million light-years. Cepheids are bright, absolutely, but even they become simply too faint to detect reliably beyond a certain distance. Past 100 million light-years, the signal just gets lost in the dark.
And hitting a wall at 100 million light-years was a huge problem. Why? Because 100 million light-years is a mere fraction of the observable universe's true size.
By being totally blind beyond that 100 million light-year mark, astronomers were effectively missing out on the vast majority of the cosmos. They were basically trying to map an entire ocean by only looking at the puddles right next to the shoreline.
This presents us with a classic detective story mystery. The big question that kept astrophysicists up at night was, how do we measure across billions of light years, not just millions? To map the true age and scale of the universe, scientists desperately needed an even brighter, even more reliable standard candle. They needed a cosmic beacon, powerful enough to pierce through billions of light years of space and still be perfectly measurable from down here on Earth.
Section 4. The Perfect Explosion, Type A Supernovae. They found their answer in one of the universe's most violent events.
So, the crucial point is how wonderfully predictable this violence actually is. Astronomers found their ultimate standard candle in a specific exploding star called a Type 1a supernova, and it occurs in a very specific, well-understood way. Step 1. A dying white dwarf star acts kind of like a cosmic vampire, actively pulling material from a nearby companion star. Step 2. It slurps up that material until it reaches an exact, precise mass limit. And step 3, because it hits that exact same mass limit every time, it detonates with almost identical brightness every single time. It is a perfectly consistent cosmic detonation.
Because their true brightness at the moment of explosion is remarkably consistent, astronomers realized they could use these Type Ia supernova exactly like the Cepheid variable stars, just on a massively upgraded scale. Where Cepheids fade out and become useless at a few million light-years, the sheer power of a Type Ia supernova allows it to shine brightly and clearly across billions of light-years. They really are the ultimate cosmic lighthouses.
And this brilliantly illustrates exactly how simple and elegant the actual math is. Whether you are using a Cepheid variable to measure out to 100 million light-years or a Type 1a supernova to measure across billions of light-years, the fundamental method is completely identical. You compare its known true brightness to its observed dimness here on Earth. By measuring exactly how much the light has dimmed over its long journey to our telescopes, we can calculate the exact distance it traveled. It's the exact same tool set, just with a much brighter bulb.
I want to leave you with this final provocative thought. Isn't it absolutely incredible that the universe's most violent explosions are the exact keys we need to measure our place within it? We started with Lemaire and Hubble deducing a beginning. We hit that frustrating distance wall where our standard tools simply faded into the dark. But by looking deeper and really understanding the precise explosive mechanics of dying stars, we unlocked the ability to measure the cosmos across billions of light-years. It shows that whenever we hit a wall in understanding our universe, the universe itself often provides a spectacularly brilliant tool to help us break right through it. Thank you so much for joining me for this explainer. I really hope this sparked your curiosity.
When you look up at the night sky, how do you actually measure the distance to a star? We can't exactly stretch a tape measure across the void, so we have to get creative. Astronomers built a clever workaround called the cosmic distance ladder. It's a series of overlapping techniques where each specific measurement gives you the baseline to calculate the next one out. Looking at this scale diagram, we start locally. We use a geometric trick called parallax to gauge the distance to nearby stars. From there, we calibrate our measurements of specific pulsing stars, called Cepheids, to map our neighboring galaxies. And to reach into the deepest voids, we extend the scale a third time. By tracking the light from Type 1a supernovae, exploding stars that burn with a very specific known brightness, we can track galaxies billions of light-years away. Without charting our immediate stellar neighborhood to build that initial baseline, we would have absolutely no mathematical way to grasp the massive scale of the wider cosmos. In the 1990s, astronomers used those distant supernovae to map the outer edges of the universe, expecting to see the expansion slowing down under the pull of gravity. Instead, the data contradicted their calculations. This graph plots the speed of the universe's expansion over time. Where the line curves sharply upward at the end, it shows that the expansion of the universe is actually accelerating, speeding up as time goes on. To explain this phenomenon, physicists introduced the concept of dark energy, a mysterious force actively pushing the cosmos apart. The discovery of an accelerating universe was significant enough to earn the researchers the Nobel Prize in Physics in 2011, but dark energy also highlighted a gap in our understanding. While the distance ladder could track how the universe is moving now, pinning down the actual age of the cosmos required a firm anchor at the other end of time, direct proof of the Big Bang itself. To find that anchor, we have to look back to 1965, when physicists at Princeton University were deliberately hunting for evidence of the universe's beginning. They theorized that the initial heat of the Big Bang would have cooled over billions of years into a faint, ubiquitous afterglow of microwave radiation. 30 miles away at Bell Labs in New Jersey, Arno Penzias and Robert Wilson were working with a highly sensitive radio antenna. Penzias and Wilson were radio astronomers focused on satellite communication research, using the sensitive equipment to optimize signals for Bell Labs. It is a striking irony of science. While the theoretical team at Princeton was scanning the heavens for the dawn of time, two engineers just down the road were struggling to get a clear radio signal.
The problem at Bell Labs was a persistent low-frequency hiss that contaminated every signal their antenna received. The noise was maddening. It came from every direction at once, it never stopped, and it remained completely unchanged no matter how they adjusted the electronics. They spent months checking for interference from local radar, military broadcasts, and even the nearby city of Newark. In a final, desperate attempt to clean the equipment, they even climbed inside the giant horn to scrub out layers of pigeon droppings, assuming the birds were the source of the static. Even with a pristine antenna, the strange signal remained exactly the same. Their inability to clean the signal was actually a massive breakthrough. It proved the noise wasn't coming from the antenna or the Earth. It was an omnipresent feature of the universe.
Unbeknownst to them, the hiss Penzias and Wilson were trying to eliminate was the exact signal the Princeton team was looking for. They had found a first direct measurement of the Big Bang itself, the cosmic microwave background. This persistent static was the literal afterglow of the universe's birth, cooled over billions of years into faint microwave radiation they accidentally captured. This accidental discovery provided the firm starting point cosmologists needed to finally anchor the entire cosmic distance ladder. Modern cosmology is built on these two foundations: the meticulous step-by-step math of the distance ladder and the sheer serendipity of the microwave background. We needed both the calculated methodology that revealed dark energy and the pure luck that proved the Big Bang to understand our expanding universe. It shows that the universe reveals its secrets through our most rigorous measurements, provided we are willing to listen to the background noise we initially try to scrub away.
Because honestly, we're looking at one of the ultimate cosmic detective stories. We're going to explore a series of observations that completely shattered our understanding of reality and literally redefined our entire place in space.
Imagine just for a second being a scientist back in the 1920s. For all of human history up to that exact point, the entire known universe basically consisted of our own local stellar neighborhood. That was it. But what happens when the universe you thought you knew suddenly gets much, much bigger? Reality gets totally upside down.
Okay, let's dive into this first section, Beyond the Milky Way, a universe unveiled.
At the time, astronomers were looking up at these weird, cloudy smudges in the sky, like Andromeda. The prevailing thought? Everybody just assumed these were gas clouds hanging out within our own galaxy. But Hubble proved this meant Andromeda couldn't possibly be part of the Milky Way. It had to be an entirely separate galaxy, just floating out there in space, far, far beyond the edges of our own.
Think about that scale for a second. In one single discovery, Hubble had proven the universe was vastly larger than anyone had ever imagined. It was filled not with just one galaxy, but with countless separate galaxies, and each one potentially containing billions of stars. Talk about a mind-bending realization.
Let's look at Section 2, the color of light, Hubble's next clue.
This was undeniably one of the most significant moments in the entire history of science, and remarkably, Hubble wasn't even close to finished with his most important discovery. He kept measuring distances to more and more galaxies using Leavitt's Cepheid method. But he also started measuring something else entirely. He started looking at the actual color of their light.
Specifically, Hubble was measuring something called redshift. So what is that? Well, it's a shift in a galaxy's light spectrum toward longer, redder wavelengths. It's actually incredibly similar to how a siren's pitch drops as it moves away from you down the street.
Now, what's really interesting about this slide is our third section, Understanding Doppler Shift in Sound and Light.
Seriously, think of an ambulance or a police car speeding past you. As it approaches, the pitch of that siren is super high, right? But the second it passes you, that pitch instantly drops. That audio drop is the perfect everyday equivalent of what redshift is doing with light.
We call this effect the Doppler shift, and it applies to light exactly as it applies to sound. It acts like a universal speed trap for light moving across the cosmos.
Look at the stark duality here. It's really straightforward once you visualize it. If a galaxy is moving away from us, its light stretches out toward the red end of the spectrum. But if it's approaching us, that light compresses toward blue.
Let's move to and see how this builds in Section 4, the grand pattern, the universe in motion.
When Hubble looked at his data, he noticed something absolutely extraordinary. Nearly every distant galaxy he measured showed redshift. Let that sink in for a moment. Almost all of them were moving away from us, literally in every single direction he looked.
And even more remarkably, Hubble found a very clear pattern in all this movement. It turns out, the farther away a galaxy was, the faster it appeared to be receding from us.
Distance and speed were directly, mathematically related. It wasn't random at all. This undeniable connection was the final, critical piece of Hubble's puzzle.
Which brings us to the climax of our story in Section 5, an expanding universe, the ultimate conclusion.
The year was 1929. This was the monumental year when Hubble formally published this groundbreaking mathematical relationship,
which is now famously known as Hubble's law. So the crucial point is, he was proving with real observational data that the universe itself is expanding.
Proving, with real observational data, that the universe itself is expanding. I really want to emphasize that. This wasn't just some clever theory or mathematical guess. It was a physical reality, forged from hard, undeniable data points, pulled straight out of the night sky.
Which leaves us with a fascinating, truly massive question to end our explainer today. Think about it. If everything is moving apart, if the universe is actively expanding today, getting bigger and bigger every single second, what does that mean if you run the clock backward? What does that mean about how it all...
Let's jump right into something that literally humbles the human mind, the cosmic yardstick. Think about it. How do we actually measure the sheer, awe-inspiring scale of the cosmos? Today, we're going to trace humanity's journey from a 17th century astronomer's basic telescope all the way to the most advanced tech in space right now, which, spoiler alert, is currently uncovering a deeply perplexing mystery about the very fabric of our reality.
Look at this number, 93 billion.
That is the size of the observable universe in light years. Now, when you hear a number staggeringly large like that, your first instinct is probably to assume it's just a wild guess, right? Like some rough estimate used just to give us a vague sense of scale. But I want to strongly emphasize right out of the gate, absolutely not. There's no guessing here. This 93 billion light-year measurement is a precisely calculated figure directly derived from rigid, testable, and observable physical laws.
So, how can we possibly measure something this unimaginably vast? Obviously, we can't exactly run a tape measure from the Milky Way to the edge of the observable universe. Well, the answer lies in two foundational pillars of physics. That 93 billion figure, it is perfectly calculated from the measured rate of cosmic expansion, basically how fast the universe is stretching out, combined with the absolute speed limit of the universe itself, the speed of light.
Okay, let's dive right into this first part, the cosmic yardstick.
To understand how we're measuring the edge of the universe today, we have to look back at how we actually built this yardstick in the first place. Every single piece of our cosmic calculations, the age of the universe, its total size, its expansion rate, literally every piece traces directly back to this exact number, 299,792 kilometers per second, the speed of light. It's the absolute bedrock of modern astronomy. If we didn't know this exact number, the entire scale of the cosmos would just be a total mystery to us.
And how we got that number? It's like this incredible relay baton passed across centuries. It all starts way back in 1676. A Danish astronomer named Ole Romer was meticulously watching the moony Io disappear behind the planet Jupiter. By timing those eclipses, Romer realized light wasn't instantaneous. It actually had a finite speed. That right there was the first meaningful measurement of the speed of light. Fast forward to 2022, and humanity is launching the James Webb Space Telescope, JWST, pushing those exact same principles to the absolute limit to look back to the dawn of time.
I really want to focus on the human element here, because it's pretty amazing. From a Danish astronomer in the 1600s shivering in the cold watching a moon vanish behind Jupiter, to a hyper-precise modern figure describing the entire scale of a 93 billion light-year cosmos, this is a single, continuous chain of human discovery. It is one long, unbroken lineage of measurement, where each generation of scientists builds directly upon the math and the observations of the folks who came right before them.
Which brings us to our next chapter. JWST pushes the limits.
Because you see, this continuous story is definitely not finished yet. In 2022, humanity's newest and most powerful eye on the universe, the James Webb Space Telescope, began pushing this measurement chain further than we ever thought possible. And this brilliantly illustrates a concept called redshift. Since the universe is expanding, light from distant galaxies gets stretched out as it travels through space, shifting it toward the red end of the spectrum. By measuring that redshift, astronomers can figure out both the age of that light and exactly how far away those early galaxies are.
And using this exact method, JWST has found galaxies with extraordinarily high redshift values. So what does that actually mean for us? It means the light we're seeing left those galaxies when the universe was less than 400 million years old. Now, in the grand 13.8 billion year timeline of the cosmos, 400 million years is literally just a blink of an eye. JWST is showing us some of the very first galaxies ever to form in the entire universe.
But these early universe discoveries aren't just giving us stunning new desktop wallpapers, they are actively challenging and refining our models of the early universe. It goes to show that even a number as historically settled as our cosmic yardstick is still being actively measured, tested, and improved today. Science never just stops and says, good enough.
And that leads us to the final, most exciting part, the Hubble tension mystery.
Now, what's really interesting here is that right as we're refining these numbers, a sudden, thrilling snag has appeared in our continuous chain of measurement. At the very heart of modern cosmology, we've got a problem. Astronomers rely on two completely different methods to measure the universe's expansion rate. On one side, they use the cosmic microwave background. That's the lingering radiation from the Big Bang itself. On the other side, they look at nearby Type 1a supernova, which act like these highly predictable standard candles in a relatively modern universe. Both methods are super robust. Both have been checked and double-checked. But they're giving us slightly different answers.
Let's clearly break down this Hubble tension, as it's called. Method 1, relying on the early universe's cosmic microwave background, suggests a specific rate of expansion. Okay, makes sense. But method 2, measuring the local, more recent universe using those supernovae, suggests a slightly faster rate. According to our current understanding of physics, these two numbers should align perfectly. But they absolutely don't. The The supernova method is consistently telling us the universe is expanding faster than the early universe background radiation says it should be.
So the crucial point is this quote right here. The discrepancy is small but real and deeply puzzling to physicists. This isn't just a rounding error, folks, or some smudge on a telescope lens. It is a genuine, documented gap in the math that directly challenges the certainty we just spent centuries building up.
And that leaves us with this massive, unresolved physics cliffhanger. Why does the universe's expansion rate differ depending on how we actually measure it? Are early universe measurements slightly off? Are the local standard candles tricking us somehow? Or, maybe most excitingly of all, is there entirely new, undiscovered physics at play here? Some completely new cosmic force? Right now, nobody knows exactly why our cosmic yardstick is acting up. But as we keep pointing tools like the James Webb Space Telescope out into the dark, one thing is for sure.
History. It's a story of how an incredibly simple, almost naive question, just how fast does light actually travel, unlocked the literal size and scale of the cosmos. Now, you might be looking at this and wondering, what on earth does a lantern from 1638 have to do with dark matter? Well, when we talk about the cutting edge of astronomy today, we're usually discussing invisible forces that shape our universe. We're trying to figure out the bizarre behavior of dark matter and dark energy. But to even begin to understand those massive unseen forces, we first had to measure something right in front of our eyes, light. And that quest started all the way back in 1638 with a very basic piece of technology, a lantern. You see, right now in science, there's a real tension in the data coming back from the edge of the universe. Things just don't always add up perfectly. And this tension might point towards some undiscovered physics, a gap in our understanding of dark energy, dark matter, or the fundamental structure of the universe itself, still waiting to be resolved. But to even measure that gap, to know for sure that something is missing, we rely entirely on the speed of light as our baseline. So let's head to section 1, the starting line, to see exactly how this whole thing kicked off. It actually started with Galileo. He tried to measure the speed of light by having two people stand on distant hills with covered lanterns, basically just flashing them back and forth. Honestly, it completely failed. Light is just way too incredibly fast for human reflexes to measure over a couple of miles. But, and this is key, that failure wasn't a dead end. It was the vital realization that the problem simply needed much, much bigger distances. It's like a giant puzzle where every method, every experiment we've covered, built directly on the one before it. Galileo's failure showed the problem needed bigger distances. Roemer's success showed exactly where to find them, in space, specifically by watching the moons of Jupiter. And then Bradley's aberration confirmed Roemer independently. The picture was finally getting clearer. Once those massive astronomical distances proved that light actually had a speed limit, Fizeau and Foucault brought the measurement down to Earth, using spinning mirrors and gears. Then Albert Michelson stepped up. He refined it to breathtaking precision, decade after decade, through sheer persistence. Which brings us right into section 2, the master key. And once that exact number was locked down, it stopped being just a fact about light. It became a universal ruler. Because think about it, if you know exactly how fast light moves, and you know how long a beam of light has been traveling to reach your telescope, you suddenly know exactly how far away the source of that light is. That universal ruler became capable of measuring the distance to stars, galaxies, and the edge of observable space itself. Bessel's parallax measurement gave us our first real cosmic distance. Then, Henrietta Swan Leavitt's overlooked, underpaid work gave us standard candles capable of reaching millions of light years further than parallax ever could. Ultimately, Hubble combined all of it, proving other galaxies exist and proving the entire universe is expanding, using nothing but careful, patient, repeated observation through a telescope. Let's step back for a moment and really absorb what we've walked through. A question that once seemed almost unanswerable, how fast is light, became the master key to understanding the entire universe. By figuring out the speed of light, we literally unlocked our ability to see back in time, to measure the gaps between galaxies, and to map a dynamic, growing cosmos. But as we'll see in section 3, this is an unfinished story. Which means the story that began with Galileo's failed lantern experiment in 1638 is, in a very real sense, still being written today by scientists actively working on this exact problem. As they use this universal ruler to probe the gaps in dark matter and dark energy, the master key has unlocked.
All right, let's dive straight in. Have you ever actually stopped, looked up at the night sky, and wondered, how on earth do we actually know what we know about the universe? I mean, we throw around these massive cosmic numbers all the time, right? But the story of how we scored the ultimate snapshot of the cosmos is honestly one of the most fascinating human achievements ever. So today in this explainer, we're going to look at the exact mechanisms and the sheer human willpower that went into literally measuring the infinite.
Okay, so the foundation of our modern understanding didn't actually come from some perfectly planned, flawless experiment. Actually, scratch that. It came from static. Literally. Penzias and Wilson's accidental discovery of leftover radiation from the Big Bang gave us a direct, undeniable snapshot of the infant universe. They were just looking for one thing, and boom, they stumbled right into the literal afterglow of creation.
And with that incredible snapshot came something else, a way to precisely calculate the universe's true age. Because of that accidental cosmic echo, scientists realized they could trace the whole timeline backward. And that brought us to an incredibly specific number, 13.8 billion years. We didn't just pull that figure out of thin air or guess it, we calculated it directly from the universe's own infancy.
But, to measure the cosmos, time is really only half the equation. You also need the ultimate cosmic speed limit, which is exactly 299,792 kilometers per second, the exact speed of light. When we start measuring the universe at these scales, we aren't using vague estimates or ballpark figures. We're using hyper-precise exact numbers that quite literally define the fabric of reality.
Which brings us right back to our timeline, 13.8 billion years. When you combine the absolute speed of light with the true age of the universe, you really start to grasp the absolute, mind-boggling scale we're dealing with here. This isn't just a span of time, right? It dictates exactly how far light could have possibly traveled since the very beginning of everything. And that brings us to a final, almost unimaginable scale, 93 billion light-years. That's the diameter of the observable universe. When you just sit there and truly think about a number that massive, it forces a pretty sharp contrast in your mind. It begs a very specific and honestly almost uncomfortable question about just how tiny we are in comparison to the whole shebang. So that leads us to this. Who actually handed humanity these answers? Seriously, think about it. Did a supercomputer just spit out these mind-bending figures? Did an advanced alien intelligence come down and explain the scale of the universe to us? I mean, how on earth did a species confined to a single, tiny, pale blue dot figure out the exact diameter of the observable cosmos? While the answer is genuinely humbling, no supercomputer handed humanity these answers. No alien intelligence explained the universe to us. Every single number we're talking about in this explainer, the 299,792 kilometers per second, the 13.8 billion years, the 93 billion light years, was measured by human beings, using instruments they built with their own hands. Every figure came from patient observation and careful mathematics. Every single piece connects, and that's what makes this so cool. Nothing here required blind faith or unfounded speculation. Every single claim traces back to a specific, real, repeatable experiment, conducted by real scientists with real, verifiable results. It's a powerful narrative precisely because it's not about just assuming things about the universe. It's a story about proving them, one careful measurement at a time across 4 whole centuries. And honestly, this brilliantly illustrates the danger of assumptions. Let's look at Aristotle for a second, obviously one of history's greatest minds. He assumed light was instantaneous for 2,000 years, and practically nobody seriously challenged him. It took repeated, stubborn experimentation to prove one of history's greatest minds simply wrong. It required the willingness to question deeply held assumptions, regardless of who originally made them.
That historical hubris reveals the real hero of our story today, because that is arguably the deepest lesson buried inside this entire narrative. It's not the specific numbers themselves, as incredible as 93 billion light-years is, don't get me wrong, but it's the actual method that produced them.
It's the ultimate algorithm of scientific progress. Question assumptions, build better tools, measure again, refine, repeat. It is just that simple, and at the same time, just that relentlessly demanding. This right here is the engine that drives humanity forward. Because when you follow that loop relentlessly, every single piece connects. This repeatable, totally stubborn process is exactly what generated 4 centuries of real, verifiable results. It took blind faith and replaced it with verifiable truth, piece by piece. But look, This isn't just some history lesson about Aristotle or the mid-20th century. This exact same scientific method is actively working right now, today. The algorithm absolutely hasn't stopped. Today, the James Webb Space Telescope is out there, actively proving those earlier steps. It is detecting galaxies that are older and farther away than anyone predicted just a few years ago. We literally built a better tool. We're measuring again, and we're observing phenomena that force us to refine our understanding all over again.
The reality is, the James Webb Space Telescope is actively rewriting parts of the story as you watch this explainer. The universe's boundaries, its earliest moments, they're being actively rewritten right now. The method continues. So the next time you look up at the night sky, ask yourself, what unquestioned assumption of today will be rewritten by the stubborn?
Welcome back, everyone. Okay, let's dive right into this because today we are looking at the night sky in a completely different way. You know, we usually think of astronomy as kind of passive, right? Just looking up. You go out on a clear night, stare up at the Milky Way, and just observe whatever happens to be out there. But what if our entire understanding of the cosmos actually came down to one exceptionally stubborn, centuries-long quest to answer a single question? It's honestly a fascinating story of human ingenuity, and it completely shifts how we interact with the universe around us. We are definitely not just bystanders in this cosmos. So here is that question. How fast is light? I know. It sounds almost like a trivia question today, right? Something you might learn in a middle school science class and just immediately file away. But as you'll see, plunging straight into the seemingly simple question reveals a reality that is way more complex and honestly far more beautiful than it first appears. Because asking how fast light moves isn't just about speed. It's actually about unlocking the very dimensions of reality. To get us started, I want you to consider this thought. The next time you look up at the night sky, remember, every single point of light you're seeing isn't just old light from a distant past, as we explored in our earlier explainer. We're reframing those stars entirely today. They are so much more than just a grand history lesson playing out above our heads. Actually, it's also a direct physical piece of evidence. It's an active part of an unbroken chain of measurement. When a photon hits your eye or hits the lens of a telescope, it is physically interacting with you after a journey of thousands, millions, or even billions of years. We aren't just passively watching a light show here. We've spent hundreds of years actively dissecting the universe, using that exact physical interaction, that light, as our ultimate tool. So let's map out this incredible journey of human measurement that we're about to trace. We're going to follow this unbroken chain across 3 distinct eras. We'll start way back in the past, in the year 1638, on an Italian hillside. Then we'll leap forward 4 centuries to the incredible, highly engineered spacecraft of our present day. And finally, we'll look to the future, to the monumental discoveries that are still just waiting for us in the dark. It's a timeline that perfectly illustrates how one single spark of curiosity can cascade into an absolute revolution in our understanding of nature. All right, let's transport ourselves back to that first point on the timeline, 1638. Picture this. You're standing on an Italian hillside at night. This is where the brilliant astronomer Galileo Galilei attempted a remarkably simple experiment. He and an assistant stood on distant hills with covered lanterns, basically trying to measure the time it took for light to travel between them by flashing the lanterns back and forth. By all practical accounts, as an attempt to capture the speed of light, this was a completely failed experiment. Light travels at an astonishing 300,000 kilometers per second. That is simply too fast for human reflexes and wooden lanterns to catch. But, you know what? The failure wasn't really the point. Galileo never actually got his answer from those wooden lanterns on that hillside. But the question he asked, how fast does light actually travel, that was entirely revolutionary. Before this exact moment, a lot of brilliant thinkers just assumed light was instantaneous, that it didn't travel at a speed at all, but just sort of existed everywhere at once. By merely insisting that light had a finite speed, a speed that could, theoretically, be measured, Galileo completely shattered that assumption. He literally set the stage for everything that followed in modern physics. So the crucial takeaway here is this, that one simple inquiry unexpectedly unlocked our understanding of, well, everything. By figuring out how fast light travels, we eventually built the ultimate cosmic ruler, the light year. Because light takes time to travel from one place to another, measuring its speed gave us a totally reliable yardstick for the cosmos. It ended up revealing the sheer size of everything that exists, allowing us to map out entire galaxies. It revealed the age of everything that exists, because seeing further away literally means looking further back in time. And ultimately, it gave us the clues to the origin of the universe itself.
And this really illustrates just how far that cosmic ruler has taken us. We have gone from the humble beginnings of two men with covered wooden lanterns trying to signal each other in the dark to the present day, a spacecraft observing galaxies born just 400 million years after the beginning of time. Just let the sheer scale of that contrast sink in for a second. We have built an unbroken chain of measurement, a continuous, obsessive refinement of our tools and our math, stretching all the way from a grassy hill in Italy to the very dawn of the universe. But what actually connects those two massive extremes? Well, it's exactly this: 4 centuries of stubborn human curiosity. This is what 4 centuries of stubborn human curiosity actually looks like. It's the absolute refusal to stop asking questions when the first answers just aren't enough. The escalation from lanterns to ground-based observatories and eventually to space telescopes orbiting our sun, it didn't happen by accident. It wasn't just some passive technological drift. No, it was driven entirely by our relentless, almost obsessive need to figure out exactly how the universe works, millimeter by astronomical millimeter. So let's move forward and see how this builds into our present day. You might think, with those advanced spacecraft, we finally have it all figured out, right? But we don't. This brings us to a current frontier in cosmology that remains completely unsolved: the Hubble tension. When we try to measure how fast the universe is expanding today, our methods clash. Measuring the early universe's cosmic microwave background gives us one speed, but measuring the late universe using exploding stars, standard candles like supernova, gives us a faster speed. Both of these methods fundamentally rely on measuring light, but the answers simply do not match. The Hubble tension remains entirely unsolved. It's a glaring reminder that despite all our precision, massive unknowns still exist out there. And you know, the Hubble tension isn't the only mystery we've stumbled into. By using light to measure the redshift of distant galaxies, we discovered dark energy. This is a massive component of our universe that remains fundamentally mysterious. We know it's there, and we know it's accelerating the expansion of the universe, pushing the very fabric of space-time apart faster and faster. But we truly, honestly do not understand what it is or how it works. The chain of measurement that started with Galileo has brought us face to face with the humbling fact that the universe still holds profound paradigm-shifting secrets. Now, to me, this is the absolute thrill of science. Because the Hubble tension is unsolved, and because dark energy remains so fundamentally mysterious, there are almost certainly discoveries waiting right now that will completely reshape this story. It means the book isn't closed. Whoever makes the next great explainer about this topic 50 years from now will undoubtedly have to tell this exact same story entirely differently, all thanks to the discoveries waiting just over the horizon, out there in the dark. Which brings our explainer full circle, right back to the very beginning. And it started with a question so brilliantly simple that a child could ask it: how fast is light? Yet it was the exact spark that ignited 400 years of relentless investigation, pushing humanity to look further and measure more accurately than anyone in 1638 could have ever dreamed possible. But here is the breathtaking irony of it all. It turns out answering that simple question honestly required measuring the entire universe itself. From Galileo's lantern to the edge of time, our quest.
Like the video. Make sure to hit that like button and subscribe for more content like this. Thanks for watching. See you in the next one.